I am going to talk to you tonight about the latest NASA mission that was launched a month ago called the Parker Solar Probe. But before I do, Dr. Klumpa, Eric Klumpa, started these Star Party talks, I think in 1999, thereabouts. So we've been doing this quite a long time, and it's a lot of fun. We want these to be informal, casual, so please stop me, ask questions if you have anything as we're going. I want it to be as interactive as possible, and I'm going to try. I always try something before I test it, and I'm always nervous whether it's going to really work or not, so we'll see. So Parker Solar Probe, again, this is NASA's most recently launched mission to study our sun. So there's the official Parker Solar Probe patch. I guess you can download one of those and print it up. They didn't give me any patches. They gave me a pizza. Just a few basic facts, and I'm going to go through some of the spacecraft details and some of the mission details as we go. So it was launched last month. It's a 7-year mission. It is, as NASA is saying it, it is humanity's first mission, dedicated mission to our sun. It's about time, I think. It is going to, it's actually quite difficult to get to the sun, believe it or not. When you launch from Earth, we're moving so fast, to slow down, to get close into the sun, takes a fair amount of energy. And the way we do it is we use gravity assists. But this is sort of reverse. We normally gravity assist to go out, but we're going to gravity assist to go inward. And to do that, we're going to use Venus. And we'll fly by Venus 7 times to alter the orbit to get us down close to the sun. So the main mission will have 24 orbits of the sun, and as you'll see, they'll get closer and closer and closer into the sun as the mission goes on. The probe itself is going to be in an environment, a nasty, nasty environment out in space, close enough to the sun where the side of the spacecraft facing the sun will be 2,500 degrees. That melts a lot of things normally, so they've got to protect this spacecraft. And you see the overall size is about 3 meters. It's not very big. Here's a meter. 3 meters. And the diameter, if you kind of look at it as a cylinder, the diameter is about 1 meter. And it only uses 400 watts of energy. Of course, there's lots of energy coming from the sun, so the solar panels will be able to use that energy. And when it gets to its closest point, in its orbit, it will be traveling faster than any other spacecraft, 430,000 miles an hour. So it's going to be moving quite fast. Parker, who is this? Why? Why did they name it after him? He is a astrophysicist, but mainly a solar astrophysicist, who coined the term solar wind. And he did most of his work studying the plasma that is the solar wind, helping us understand how the energy gets off the sun, out into space, and out towards Earth. This is also the first mission, so they've named many missions after famous people or prominent scientists, but this is the first mission that I'm aware of, that I read, that the person that it was named for was alive to see the launch. So he's 91 and still going, I guess. So he is also given credit for the way the solar wind, because the sun is rotating, the way that solar wind sweeps around and expands outward is a spiral-shaped pattern. So he's given the distinction of the solar wind spiral pattern as a Parker spiral. So that's where why the mission is named the Parker Solar Probe. And so we'll talk a little bit about some science and some of the engineering that was involved in the spacecraft. But why do we want to study the sun? Well, we're in a pretty unique position to study the sun. We're close enough, but not too close. And we're now in a position to launch spacecraft even closer. So the sun, of course, is very important to us, to life. We can study this star and apply what we understand of this star to all the other stars. So obviously that's a big importance. So this solar wind, this energy, these charged particles, this radiation environment, how does that work? So that's one of the ultimate goals of this mission, to try to understand the origin of the solar wind and how it interacts with, if we understand the origin of the solar wind, then we can better understand how it will interact with Earth and other planets, we call space weather. So what are the conditions in space between the sun and the planets? And surprisingly now, that's pretty important. It wasn't so important, but now that we have lots of spacecraft in space, now that we have humans, by and large, permanently in the space environment, and we're planning on continuing that, my understanding, I don't think humanity is going to stop exploring. So we need to understand this environment better. So that's another goal. And the interaction of the space weather, the space environment with the planets is also part of the why we're doing this. So here are the key science questions. Again, what is the origin of the solar wind? So we know what it is. We know its composition. So it's plasma. It's just charged particles, electrons, protons, even heavier elements, helium, lithium, nuclei, those kinds of things. But by and large, it's protons, electrons, and helium nuclei. And these guys are moving quite fast in space, throughout space, and this wind, the particles have reached, because the sun is hot enough, these particles will attain velocities high enough for them to escape this big gravity ball we call the sun. So that continuous flow of particles from the sun is the solar wind. So that's the one question, is the origin of the solar wind. How do those particles get sped up in this environment? And one of the most fundamental questions, well, I would say in solar physics, is how in the world does this corona, so I'll show you some pictures of it. Larry down here took a great one. I'll show you one of his from the solar eclipse last year. How does this atmosphere of the sun, how is it so hot? It's actually hotter than the surface of the sun. We don't know the answer to that. So the Parker Solar Probe is hoping to determine that answer. So that's the fundamental science behind why we're doing the mission, or why NASA is doing the mission. And in doing so, there's 4 experiments. There's a camera got to have a camera. It's just one of those things that if you don't take pictures, you don't get funding, right? I mean, and that's ultimately our money, right? Yeah. So it's okay. There's been some fantastic discoveries because a camera has been on board certain missions. So the camera is going to take some fantastic pictures up close. There is an experiment to study the electric and magnetic fields. The solar magnetic field is extremely dynamic, and the Parker Solar Probe will be right in there in some of those fields, so it will be able to measure that directly. And then the other two, this integrated science investigation of the sun and this sweep experiment, those are measuring directly these charged particles, so low energy and high energy. Again, to help us understand why, how those guys are being accelerated so fast. So that's the 4 experiments, and you see them on the spacecraft there. Just a little bit of background about the sun. So we know, understanding some basic physics, what the interior of the sun is like. It has essentially, we have a surface of the sun, even though it's not a true surface, because it's a big ball of gas held together by gravity. But in the interior, you've got 3 basic layers. You've got the core, which is distinguished because that's where the nuclear reactions are happening. So hydrogen, by and large, hydrogen is being fused into helium and producing energy. So that's the main energy source. There's other nuclear reactions going on as well, but it's a fusion system. And then there's 2 transport zones, this radiation zone and convective zone, to get you to the surface, which we call the photosphere. And when you take a picture or you see it under the right cloud conditions or at sunsets and things like that where it's safe to look at it, that limb, the ball of the sun that you see as the limb, is the photosphere. That's essentially where the gas of the sun gets thick enough, we say optically thick enough, you can't see through it. Up to that point, it's transparent. Then it gets to a point where it's not transparent, and that makes a very clear surface called the photosphere. And then you have this chromospheric layer right above the photosphere, and then the outer atmosphere we call the corona. And this diagram here came from some of the Parker materials, but it shows you some of the temperatures. And I won't talk about the densities, it's not that important here, but from the core, you see 27 million Fahrenheit. You've got to have that kind of condition for these nuclear fusion reactions to work. That's why it's so hard for us to do nuclear fusion here on the Earth. You've got to have that kind of, those kinds of temperatures for these reactions to take place. Then you've got, again, these 2 transport zones. So radiation, a radiation zone, what does that mean? Well, you're transporting energy by essentially electromagnetic waves. So how does the sunlight get to Earth? How does it warm us up? By radiation. We're not touching the sun, so that energy through electromagnetic waves is hitting the Earth, warming us up. So that's the same transport mechanism that's happening here. And then the gas gets dense enough, then it starts to boil like a pot of water. So you get convection bubbles boiling. And you see the temperatures are getting cooler as you go outwards. So 3.5 million, 3.5 billion, and you get up to the very surface of the sun, and relatively speaking, it's much, much, much cooler. 10,000 degrees rather than millions of degrees. But then you go off the surface of the sun, so there's the photosphere again. The chromosphere is a very thin layer that has this kind of beautiful reddish color. You can see that during eclipses or artificial eclipses. And it's about the same temperature as you see as the photosphere. Then you get out into the corona. So somewhere there's this transition zone. You go from 10,000 to 2 to 5 million. Now the gas is getting dense, less and less and less dense as you go outward as well. So the temperatures are high, but it's a little bit of a strange way to think about energy. So part of the reason, well, let me explain that a little bit later. But the temperatures are high because the particle motions there, even though there's very few particles, the particle motions are extremely high. You just don't have that many. So imagine sticking your hand into a pot of hot water, right? You're touching that water and it's immediately hot. But if you stuck your hand into, so 100 degree, or 100 degrees C, 212 degree Fahrenheit pot of water, and then you stuck your hand into a 212 degree oven, not touching the oven elements or anything, just in the air. You're not going to feel it as fast. I mean, eventually. But so that's sort of a similar situation when you're near the sun. Even though there's not a lot of particles there, there's not a lot of air, the high temperatures are because the particles are moving so fast. So it's kind of a different way of determining energy. So temperatures are high, but it's not carrying as much heat, if you will, because there's not as many particles doing that.
Question?
Yeah.
Similar to like an airplane flying through the atmosphere, just sitting there, it's not hot, but as it races through, it heats up, the skin of it heats up, right?
Right.
Like the SR-71, you know, the Air Force in Blackbird.
Right.
I mean, it got really hot, and that's why they were concerned with the heating and everything else. So
Yes.
is that similar to what we're talking about here?
Yes, you have to have special shielding for that. And so the SR-71, you know, the space shuttle had these special heat shields coating it. But of course, as you get higher and higher in altitude, the atmosphere thins out, so it won't get as hot up there. As you get lower in altitude, there's more air, and so you're going to get more more friction, if you will. Yeah, yeah. So it's sort of a strange environment, but it's something that you still have to prepare for. And so that's the basic structure of the sun. You have these layers, and the Parker Solar Probe is going to get very, very close. I'll show you how close. And but we know the sun is incredibly dynamic. It has a solar cycle, which is a magnetic cycle. The sun's magnetic field changes constantly. It sort of twists and turns and becomes magnetically active for a few years, and then it becomes magnetically less active for a number of years. And on average, it's 11 years. And during the times when it's more magnetic, we get the sunspots. So the sunspots essentially just are a way of an indicator of how magnetically active the sun is. And then, as you see now, the sun is getting quieter. we're approaching a solar minimum. And so that magnetic cycle has something to do with studying the sun locally, as the Parker Solar Probe will. And here's our a few beautiful pictures of our eclipse last year. And you can see the corona. How many of you got to see it last year? Most of you? All right, good. What a fantastic experience. It's a year ago now, man, a year and a month. It's hard to believe. It was awesome to see the corona. I mean, just beautiful flames just rushing out from behind the moon covering the sun. It's kind of scary looking. No wonder the ancients were worried. It's like, have to behave. The sun is going to get them. But these images here, that's Jimmy is a student here, and Larry teaches here. So he was here, and then a couple others I picked up. But just an amazing amount of detail. But you also see the extent at which the solar wind fills our entire solar system, but you can see how obvious that corona is as it extends away from the sun. So Parker Solar Probe is going to get right in that solar wind and measure it. I couldn't get my movie to play on this PowerPoint, so I'm going to have to go here, and I'll see if I can. So this is a different solar. I wonder if I can repeat. This is NASA's Solar Dynamics Observatory, and this is looking at the sun and ultraviolet light, and then they color code it. I don't know if I can set this to keep playing or not. Oh well, I'll just keep playing it. But you can just see the incredible detail on this surface of the sun. All these loops and bright spots showing you where there's active regions. And these, well, I'll just leave it like this for the moment, but these loops here, here, you can actually just see these are magnetic field lines. We can't see magnetic field lines, but when there's enough gas that's sort of trapped along those magnetic field lines, they're bright enough for us to see them. So they're beautifully displayed by this hot gas. So these bright regions here will get brighter and release a tremendous amount of energy in a very short amount of time. So these are called flares. So kind of explosions, big explosions on the surface of the sun. And that energy gets released in many forms. And where you see active magnetic regions here, those are the bright points, and you can see this gas connects these regions together in some cases. So these are magnetic field lines. So these are magnetic poles, if you will, on the surface, and we're seeing the iron filings that you would see on a tabletop if you had a magnet. And this is, I believe this is 4 hours of time. No, that can't be right. That's 4 days. I'm sorry. That's 4 days in a time sequence there. But you can just see how incredibly dynamic this whole star is.
Did they use all the ultraviolet rays, or did they select
Yeah, they've got several filters on this, and they're using just a narrow band here for this one. And of course, by using narrow filters, light filters, you can essentially you're looking at different layers of the sun, different energy from the light gives you an indication of the different layers inside the sun or near the surface of the sun. So it's really quite incredible. So here's where I'm going to try my little experiment, and we'll see how it goes here. So I need a few volunteers. So anybody, I need somebody with a cell phone as well. Any volunteer? I need you to be a solar flare. Yeah, can I get a solar flare? All right. You mind coming down? So I'm going to put you over here. So you're going to be the surface of the sun. And what's your name?
Ian.
Ian.
Nice
Hi.
to meet you.
Good to meet you. So you're going to be the sun. You got a cell phone?
Yes.
Okay. And I need 2 young people. I need 2 runners. Can I get somebody to help me? Can you help me? You're going to be plasma. Okay? Come on down. Can I get somebody else to be a runner? You want to come down and help me? All right. Fantastic. What's your name? Laura?
Nora.
Nora. Hi. Nice to meet you. What's your name?
Eden.
Eden? Nice to meet you. All right. So you guys are going to stand real close to the sun here.
Don't look at me directly.
That's right. It's pretty hot over here, isn't it? And I need one more person to be the earth over here. All right, I'll let you. Here, let's do this. I'll put the earth on the chair. So the earth is way over here. Right side up here. Okay. So tell me again, I'm sorry.
Ian.
Ian.
Nora.
Nora. Eden. Okay, very good. All right, Nora, you're going to be charged particle plasma, okay? And Eden, you're going to be light, okay? So you're going to be sunlight. And when Ian here takes a flash, his camera flash, that's going to represent a solar flare. Okay? So what happens in a solar flare is energy gets thrown off the sun in many ways. One way is that it emits light. It's a big flash of light. And how fast does light travel from the sun over to the earth? How long does it take for light to travel from sun to earth?
8.5 minutes.
8 minutes or so. Okay? So we got 8 minutes. So light goes from the sun to the earth in 8 minutes. But I'm going to ask you to run. Okay? When he lets off the solar flare flash, you're going to run to the earth. Okay? Because you're light and you travel really fast. Nora, you're going to be plasma. So you're particles. So you're the solar wind. You're traveling 1,000,000 miles an hour. Right? Which is slow compared to light. So what you're going to do is I want you to shuffle like this from here to earth, okay? When he sets off the solar flare, you're going to run and you're going to shuffle. So 1,000,000 miles an hour, these charged particles are blasted off the sun, and the earth is 93 million miles from the sun. So moving at 1,000,000 miles an hour,
93 hours.
93 hours. Yeah. So how many days is that? three and a half or so. So she gets to the Earth in 8 minutes, but you get to the Earth 3 or 4 days later. Okay? You ready? You ready? Okay. So solar flare, camera flash, run, and you shuffle, 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 slower, 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 slower. Yeah. All right. Very good. All right. You guys get NASA stickers. If I can peel it. Here, you probably don't want them peeled. So let me see if I can just tear it. That way you can use them later. There you go. There you go. Thank you. You want your NASA stickers?
I won't say.
You gotta have it. Come on. There you go. Thank you. So, energy is moving, throughout space in different ways. So, light, immediate. But then this plasma, this blast of energy comes off the sun, and again, takes 3 or 4 days to reach the Earth. And that plasma, these charged particles, can, really hurt us. If you're out in space, we're protected. We're protected by our magnetic field, we're protected by our atmosphere. But if you're out in space, that wave of a flare, if that blast of energy is directed towards the Earth, we have to be careful about that. And spacecraft can get damaged. We have power outages, and things can get messy if we get a large influx of this energy. So a flare is one of the, where's my clicker here? Okay. A flare is one of these events that I'm sure the Parker Solar Probe will try to better understand, again, how that energy is flowing. So this movie was taken, in 99 you see here, but this is an artificial eclipse of the sun. So the sun is a little ring behind the blue disk there, and what you're seeing is the solar wind. And you can look at the clock to see sort of what kind of time sequence we're talking about here, on the order of hours. But that solar wind is continuous. And occasionally the sun belches, and then this blast of particles, plasma, light, energy comes off the sun. So these are called coronal ejections, but they can be triggered by a flare. And again, a flare is a tremendous release of magnetic energy right near the surface of the sun, right near those sunspots, where those magnetic field lines are all tangled up, and then they get twisted around, and they release, and then they release energy and become untangled and recombine. And when that happens, you get an incredible release of energy. And so that causes these coronal ejections sometimes to just get blasted out into space. So we're living in this wind, right? Earth and the other planets live in this wind. Here's another sort of close-up of some of these magnetic loops. This is plasma, charged particles right near the surface of the sun that are looping around these field lines. I think this is going to continue to play.
What exactly is an artificial eclipse?
Oh yeah, good question. So let me go, if I can go back here. So astronomers can build instruments. They call it a coronagraph, but it's a telescope that basically blots out the center of what you're looking at. So it covers up the sun. If you're looking directly at the sun, it covers up the sun, and then it can kind of overexpose the area around the sun, so you can see these charged particles, or see, in some cases, faint stars distant near the sun. So it's just an artificial way of looking at the environment close to the sun, where it's very difficult to do that because the sun is so bright.
Is there a preferred direction that they go? We noticed this one was down lower right. Is that associated with positions of the planets to attract them, or is it just a random sort of?
Yeah, this is random. Well, semi-random. So why does the ejections happen here or up here? So that has to do with the solar cycle, the sunspot cycle. So the sunspots start at high latitudes and sort of over the 11 years migrate towards the equator, and then they restart again. So yeah, the latitude, it's mostly mid-latitudes, but it's near the equator. But so in that sense, the probability of being in a certain latitude is higher at certain times of the solar cycle. But when a flare happens, where would it happen on the sun? I have no way of predicting that. That is very random. Yeah.
Is that something the probe is going to try to verify?
Not to my knowledge. I don't know if they're going to look at sort of the longer term magnetic, or be able to predict the magnetic activity. I think it's really how is that magnetic activity transformed, energy is transformed into the corona and in the solar wind. But again, this is just incredible movies of the churning power of the sun. And when you get a flare, I guess it happened right there. So when that flare goes off, let's see if I can stop it. This is a medium flare. You see all those particles right there? So that's also in high energy particles. So there's really I needed a third runner here. So there's a slow solar wind and a fast solar wind. So some of the particles are accelerated to extremely high velocities. And those we call cosmic rays. And that's what you're seeing here, is that those particles essentially hit the camera and slightly damage your CCD camera, and you get flashes of white light all over the picture, and then they go away. So that's a small solar flare, but you can see the beautiful loops of magnetic activity near the sun. All right, so how close is Parker going to get? So I've got the football field. So the standard analogy here. So if the sun is at one end, the earth is at the other end of a football field, so 100 yards. Venus would be here, so about 70 yards from the sun. Mercury would be at the 39-yard line, approximately. The closest spacecraft that has come to the sun was this Helios spacecraft back in the 70s. And Parker, you see, is going to make it to the 4-yard line. So by far, it's going to come closer to the sun than anything else. And if you remember those, so if this is the proper scale here, if this is the size of the sun, you saw that plasma blasted off of the sun in these coronal ejections. So it's about 9 solar radii. So here's a solar radii. So Parker is going to get, I don't know, right in here. So right in there, in that, as close as they can to understanding this solar wind. So that just gives you another picture of it. The top one there, 3.9 million miles. Yeah, that's still a long way, but compared to every other spacecraft that we've sent, that's pretty close.
I have no background in science whatsoever, but my immediate question is it possible to capture anything that close that can be brought back, that can do amazing things that we can't do where we are with the sun?
That's a good question. I don't know if it's possible. I suppose it is, because you could sort of have your collection bag, if you will, right? You're going to catch fireflies, and you zoom in near the sun and catch some fireflies, and you come back.
Seems like such an opportunity if that's possible.
Yeah, but I know that that's not the goal, right? That's not a sample return mission. It's not the goal.
Given our problem with fossil fuels and stuff like that.
Yeah. But understanding, again, how these particles work, and that will help us understand those particles when they reach Earth and beyond. But I suppose it's probably possible to do that.
Isn't it going to burn up eventually, though?
Yeah. I think the plan is after the 7 years is they're probably just going to throw it into the sun. Yeah, because it takes energy to get it back to Earth. Yeah, John?
Kind of in the same vein of this, do you know if they're anticipating like these solar ejections affecting the trajectory of the probe itself and like having to accommodate for that
Yeah,
action?
I don't know that. I mean, all spacecraft have some fuel on board to do some maneuvering. So I suspect this one does as well. So they can, most of the orbit is going to be changed by gravity from Venus, but I'm sure they're going to be able to make some maneuvers.
Coming that close, if an ejection, if like a solar flare just managed to hit square on, how would that affect the trajectory? And
Yeah.
would they have to correct it?
I don't know, because the solar wind is essentially empty space.
Right.
It may not affect it at all.
You could not, I'm just curious if
Yeah.
you anticipate any kind of, even if it's just a little nudging of some sort.
Yeah, I don't know. But I'll show you the orbit here, and you can see that they can probably make a correction as they go when they get far away from the sun. But how's this thing not going to melt? That's a common question, right? You're going to get into this environment where it's 2,000 to 3,000 degrees. How is it not going to melt? Well, just like your heat shields on the SR and then on the space shuttle, they have a heat shield. And it serves two functions, right? So this carbon composite material, it's not very thick, but it rejects the heat so much that in front of the shield, when you're on the sun side of the shield, you're at 2,500 degrees. On the other side, inside the spacecraft, it's 85. Again, that's how thin the solar wind is. And you know this. You go out and stand in the sunlight, direct sunlight, it's pretty hot. But if you put up an umbrella or something, it's quite a change. Now imagine doing the same thing without an atmosphere. Right? So the reason it's still hot underneath our umbrella is because we've got lots of air circulating around. But remove all the air and then put your umbrella up, you're in the shade, made in the shade. Yeah. So same deal. And they paint it white on one side, and that's highly reflective. So that also keeps the spacecraft a bit cooler. Pretty ingenious.
So do you think with a white surface, do you think that would kind of act as like a solar sail in a way? With all this
That's sort of getting back to John's question here. Yeah, do those particles, does a solar wind kind of push on the spacecraft? Yes, to a small degree. I don't know what that effect would be, but it's the spacecraft is pretty hefty, and those particles aren't going to move something that heavy. Yeah, but technically, yes. If you had a sail big enough, it could move a spacecraft.
Yeah, that makes sense.
Yeah, yeah. So the spacecraft is designed, so you see the solar panels out to the side. The spacecraft is designed so those solar panels will move in and out like this, and by how much light is hitting those solar panels, that keeps the spacecraft oriented properly towards the sun. Well, it'd be behind me, I guess. But so it's sort of like wings, so they just flap them in and out, and that way the attitude, the spacecraft is always, the white shield is pointed at the sun all the time. So here's the overview slide of what the orbit is. As I said, it's a 7-year mission, and then the next one I'll show you is a movie. So here's the inner solar system and the Parker Solar Probe there in aqua colored. And as you see, it's highly elliptical. So the planetary orbits are essentially circular. The spacecraft then is highly elliptical. So it comes in very close to the sun and then interacts with Venus a couple of times and then gets closer to the sun. 7 times, you see, it alters its orbit, and then it goes in very close to the sun. So not until the last 3 orbits is it going to get to the 4-yard line, per se. But it will be able to sample, and you see how quickly it moves through the near the sun. So that's just orbital dynamics there. But and there's another probe they're going to launch, I think, in 2020 or 21. It's the Solar Orbiter in green there. So they're both going to be flying at the same time there for a while. But that's how you conserve energy. The budget for this mission got cut in the early 2000s, and so they had to redesign. And now you have a lighter spacecraft. It's not going to be able to do as much. And so it's a longer mission because instead of carrying so much fuel to slow it down to get in close to the sun, now they're using Venus as a gravity assist machine. And then in 2024, the Parker Solar Probe goes away, and then the other one is still flying. So it's really kind of some cool orbital dynamics that go on in this mission and others like it. So I'll end. If you have any questions, I'll be happy to answer them the best I can. But NASA is pushing this. I was at NASA last week. It was kind of fun, and I got those from the education office, and they are really pushing this as our first mission to our star. Humanity's first mission to the sun. So thank you very much for your kind attention. I don't know what the sky is going to look like outside. If it's clear enough to see Mars or Jupiter through the clouds, the Astronomy Club has some telescopes set up. If it's too cloudy, they won't be set up. So it's easy to tell whether we're going to be out or not. Thank you. And this is our schedule. Do I have the latest? Yes, I do. Okay. So we have a small change November. Just a heads up. We have a football game on Friday night, and we did not want to compete. So we're on November the 9th for our November Star Party. So questions? Yes?
The orbit was such that it was being flung way out. So you could have put a little pouch on it and jettisoned it towards the Earth as it was being thrust back, have that little thing come back and collect
That's
some
right.
of the thoughts.
That's right. You can absolutely do a collection
The whole thing
when you're
wouldn't
close
come
there.
back, but you could do a little portion of it.
But you can collect the solar wind. It comes to you
Yes.
in a sense. So I don't know the advantage of collecting particles close to the sun and bringing them back. The point of flying through it is that you can directly measure the energy of those particles, the velocity, the energy, and what the electric and magnetic fields are at that point, and get a better understanding of the how things are working. You know, why does it happen that way?
I'm wondering about the collaboration among other nations around the world about this, since it's...
Yeah, I know this mission is headed up by Johns Hopkins. But typically, I mean, NASA's pretty good, and scientists in general are pretty good about being borderless, right? We collaborate all the time with universities in general. That's the reason I took this job, right? It's a fantastic environment to work in, right? No matter what your field. And you know, certainly the sciences are very collaborate very well with other countries, and NASA does too. I don't know on this particular mission if there are other countries involved or not. I didn't look that up.
You said it's a 7-year mission. When will we get there? When will it start?
Oh yeah, that's a great question. So the first pass by the sun is November. Yep. So it's already on its way. It won't be a close pass, but that's where it's going to have to do several orbits and get the trajectory changed by Venus, and it gets closer and closer over the years. But yeah, the first, we call it a perihelion, when the spacecraft gets to its closest point, is in November. Question up here, I think. Yeah.
Is the timing of this mission to coincide with that ebb in the solar cycle, or is it just fortuitous or not?
I think, I don't know if they were able to plan that carefully for the mission. It could be, but the fact that it is 7 years, we're going to be in a solar minimum, but we're also going to come back and get close to the solar max. I suspect it's, you just take it when you can get it. Like, when am I going to get the money to launch this thing? And when I do, I better just do it. And I'll adjust the science or do the best I can with the science.
Will they be getting any information like now or on the way, or is it right at the end?
No, so they have communications on the spacecraft, so they talk with it constantly. So they'll be able to uplink and downlink, and the experiments will be transmitting data back all the time. Yeah. So when it goes close to the sun, or maybe on the far side of the sun, of course not at that moment, but when it comes back around, then they kind of do a data dump, and then they get what all the experiments were able to measure, say over the last month or whatever. So yeah, they're in continuous communication with these. Mm-hmm.
We're visiting the solar cycles. I was noticing on your chart some were higher than others.
Yeah,
So there's some variance between one cycle and the next.
absolutely. That is.
Cycles and cycles.
Are the cycles what?
Are there like groups of cycles?
Like high, medium, low, high, medium, low, high, medium, low, or something like that?
Not to my knowledge. So the
Does that
last.
affect theirs in any way?
Well, it certainly does affect the solar output. So our star is not a constant. It's pretty close, but it is changing the amount of energy it gives off. But it's fairly regular, but it does have some variations to it. And we know that there are, we think there are some correlations with like ice ages, that kind of thing, but they haven't been able to, there's some correlations, but I don't know that there's causation with ice ages and changing suns.
Well, that's what I was asking, is the intensity or unintensity of these cycles, would that have an effect on volcanoes?
No, because that's, so it would affect, say, the upper atmosphere and perhaps the magnetic,
Gravitational effect?
right, no. No, the solar wind is essentially so thin, it doesn't affect Earth gravitationally, or it wouldn't affect the internals of the Earth, you know, the geologic nature of the Earth. But yeah, you can see, so this is, I believe these are monthly averages of sunspot numbers, and you can see there's a wide variation over months, but then you see the longer term trends where you have the 11-year cycle. Yes, they vary all the time, and as far as I understand it, we do not know why that is.
Something about an equator, you talk about the sun?
Yeah, so the equator region of the sun.
So there's more stuff going out, did you say, around the equator?
Yes.
Would this way?
Yes, because there's more magnetic activity near the solar equator. Yes, so we do know that, and again, we have these long-term cyclical effects, but the intensity of each cycle we can't predict. I mean, they have some predictions, but I don't know if they're very accurate. Yeah. Any other questions? Yeah,
Did they mention anything about taking any data from Venus being that close? Or is it just going to be specifically focused on solar data collection?
I don't know that, but I don't think so. I mean, if the experiments are on, if there's no reason why they wouldn't be able to, say, measure the environment. Well, I do know they're interested in the solar wind planetary environment, but you know, Venus doesn't have a magnetic field to speak of. It has an atmosphere, so I don't know if they'll be able to measure any variations, but certainly they'll be able to measure the particle numbers, the densities, the energies at Venus. You know, so they'll be taking data at that point, but whether they're going to correlate it with the planet, I don't know.
Venus, they're just
Not to my knowledge. Yeah, not to my knowledge. Ah, yes.
So it's the solar wind that creates our auroras, is that
Yes.
correct?
Yeah, that's right.
So when we have solar maximums, we have more intense auroras.
That's exactly right.
So
That's,
Venus would not have an aurora.
No, it has, because there's no magnetic field. So it doesn't have an aurora the way we do. But when the solar wind hits the upper atmosphere, even without a magnetic field, those particles do impart energy. Yes, it's a diffuse kind of thing. And I'm glad you brought that up, because that's a direct connection. So the solar wind and the Earth, you know, are directly connected. And one way we are directly connected is the aurora. So the beautiful northern and southern lights, that's the charged particles, some of them leaking down and hitting our upper atmosphere and causing a glow. So in a sense, Earth and the sun are tied together by this wind. I mean, the light helps too, you know, need that. Any other questions? Thank you so much for your time. And as I said, if it's clear enough, if we have telescopes set up outside, feel free to wander out there, and I'll wander out there too, and we can chat, or I'll hang around here for a few minutes if you have questions. Have a good weekend. Thank you.